Alright, hell yeah. So someone requested these I think they're AP1 FRQs, frequently asked questions. No, they're free response questions. I've never heard of this type of stuff, but it's pretty sweet. So anyway, so we have a block. This is ready to be dropped. So you're kind of like holding it in place. And this block is on a frictionless surface. And so, hell yeah, you know what I mean? To simplify this, you know what I mean, just drop this block off a cliff. We kind of all know what's going to happen there. And then how I simplify this, you know what I mean? Hey, let's not use the spring yet. How I simplify this is like, okay, so let's say you do drop this block off a cliff, but we have a pulley here, and it's actually connected to another block. Now, it's really hard to imagine this because this surface is frictionless, and there's just no such thing as a frictionless surface on Earth. And what this means is this could be the, you know what I mean, it could be the Titanic. Or I mean, it could just be like a 1 meter by 1 meter steel block. But if it's a frictionless surface, and you know what I mean, and this is you know what I mean, attached to a harness, attached to this block, even though it's just resting right there, you would think it would hold you, but it won't. You know what I mean? You'll just be going hella slow for a long time until this thing just barely moves. But it'll move, and so that's kind of the interesting thing about frictional surface. I mean, that's going to be the take-home point for this problem. It's just like, oh, never thought of that. But anyway, and so we all know what well, you should know that free fall, you change your speed by 10. That's the acceleration of gravity. 10 meters per second per second. Now, that means in 1 second, all this means is you're going 10 meters per second. Let's say you're going 0. So this is where you got to do that quick calculus in your head. We have an average velocity of 5, and you did that for 1 second. So our distance is also 5 meters. You know what I mean? So hell yeah. And but if you're actually dragging, you know, if this is 1 kilogram and this is 1 kilogram, well, you're not going to be changing by 10, you know what I mean? So I don't know, should you just kind of guess? Is it going to be 5? Is my acceleration in this, we'll just call it A now, is my acceleration here? And then even this is where this gets hella confusing, because you're like, okay, my acceleration is G. Well, yes and no. So I kind of want to move fast, but then just, you know what I mean, still hit all the points. If we have a mass right here, you know what I mean, we identify a mass, and you know what I mean, for a lot of problems, you'll just write mg. Now, where the hell does that come from? Kepler. So we have the force of gravity, gravitational constant, mass of this, that's that m, mass of the Earth, radius of the Earth squared. These three terms are g. You know what I mean? So how do you apply this to F equals ma? Well, you're going to say, what are you going to say? Hey, this is the mass that we're identifying. Okay, cool. And we want to know its acceleration. Maybe we run a little experiment and we see that it does change in velocity. Hell yeah. And then we come over here to our textbook. There's only a few things that will draw force. Electromagnetism, gravity, and so hell yeah, you type in Kepler's equation right here. So that's what goes into this side. So you basically have mg over here is equal to m, what you're analyzing, and this a, this is always your acceleration. With F equals ma, this a is your acceleration. It just happens to be, let's rearrange, it just happens to be for free fall, your a, your acceleration is just this g, this gravitational constant that has units of meters per second. Okay, hell yeah. So with that said, I think we can kind of move on to figuring out if we're dragging a second mass. How would we figure that out from F equals ma? So let's do that. If I just had straight equations, F equals ma, well now, let's type this in. Let's put Kepler over here. So we're going to go gravitation, me, radius of the Earth squared, is equal to the m that we're analyzing and its acceleration. But if these two blocks are connected, this is where any pulley situation that goes like this, I really would put it on a horizontal surface. and just pretend like it's a frictionless surface. We can imagine that, right? And then on this one, I would say that we have a force, just write it F, maybe just Fg, and then, and then write Kepler, M, gravitational constant, me, mass of, radius of the earth squared, or, we get it. The force of gravity is just mg. Now, there still is a force of gravity, but it's this way, and it's kind of neutralized by this normal force. That is not in the direction of acceleration. Hey, if this force was stronger than this normal force, maybe the ground is sinking, hell yeah, we'd have some acceleration in this direction. But we're just interested in the acceleration in the path of the string. You can straighten out the string, and you can see that this force of gravity isn't helping. Okay, hell yeah. And so, for a free body diagram, you can treat these two blocks as a unit. So you could kind of draw this picture just as one big block. That's m1 plus m2. And now this is moving, but it only has a force of m2g. So that's the only force that's on it. Okay, so can we show that with F equals ma? Yeah, I thought we were going to. Yeah. So right here, we just wrote F equals ma. We wrote Kepler over here. But what's this? This is going to be mass 2. Okay, cool. So I have, hey, we just identified that this is m2. This is all g. Cool. And then, but what's this? They got to be the total mass of everything. That's going to be the hardest thing when you're doing Pulley problems. Or even teeter-totter problems. If you do a teeter-totter problem, you have to do the same thing. Hey, yeah, you have a driving force because maybe this is bigger, and so it's whatever, if this is 1,000 newtons and this is only 500 newtons, well, you have a driving force of 500 newtons over here, but maybe, because if this is 100 kilograms, this is 50 kilograms, but this 500 newtons is moving 150, So that's going to be the take-home point message for this video. Is like, cool, you have a force, but it's moving a bunch of mass. If it's moving both of these, cool. Let's say it's also connected to, if you get like esoteric and be like, maybe these two masses are moving another bit of mass in a different dimension, and we just don't know it. But actually, that's why, and only because of that, it's, I don't know. I kind of want to get a little esoteric. That was a little bit too far. But we are going to talk about some of those things. I got to make a fast and flighty video, but we're going to do it. Okay, did we finish this off? Okay, so we have m1 plus m2. That's kind of how you can do that, A. So booyah, and then you're rearranging. But this is exactly what you want. You want the acceleration. And so we have m2g divided by m1 plus m2. Okay. All right, so now we kind of have that figured out, where we drop 1, and let's say they are 1 kilogram. So what was our acceleration going to be? We're going to have 1 times 10, that's going to be 10, divided by 1 plus 1. Oh, cool, look at that, 10 divided by 2, that's 5. All right, so we have a check on reality, but I hope I can guess wrong on some of these, because, yeah, that's when I learn the most, is when I just... say wrong things, and but yeah, hopefully we say some wrong things today, but we're doing pretty good so far. Now let's see, it says in terms only of the forces directed on block 2, explain why block 2, so they want to know why this speeds up but then comes to a momentary stop. So okay, now we got to involve the spring. Springs are very fascinating. I think the thing that people do not realize about springs, and I think the take-home message that I can impart, we just got a spring from Home Depot or whatever. No one gets springs from Home Depot. You go to Ace Hardware. Okay, but anyway, so when you have a spring, let's say it's just resting on a table, and then, you go and put your thumb down on it, and then just push on it just a little bit. So now here's the take-home message. You're going to put a little force on it, but guess what? Or I guess this is what I'm getting at. It almost takes no force. This could almost be 0, and you will move the spring just a little bit. You know what I mean? So think about that. Like almost zero force can move the spring. Now it does require a tiny bit of force, but literally zero force can move the spring right off the bat. And so just always know that. Anytime you have a spring, you could go up to it with just, even if it's just like a huge car spring. You know, it's kind of fascinating. Go up, if you hold it in your hand and do this, even if you're just doing this, you are moving it. And I think that's a very physical thing that people are not aware of. Like, and the crazy thing is you could do that for anything. You know what I mean? I could take this block of wood and just do this, and I hardly have any pressure on it, but guess what? It's compressing, you know what I mean? It is dimensionally squished, and I think that's fascinating. And even if I just put barely any force on it, you know what I mean, just kind of hold it together, it is moved, it has moved, so that's going to be the take-home point. You have a spring, even the tiniest force is going to get it to move. And the reason that I mention that and said it so many different ways is because I think it's because I think we recognize springs if I stand like on a scale. You know what I mean? Hey, maybe we kind of recognize that there's springs underneath that scale in some sort of you know, thinking. And once we step on those scales, like the springs, all right, so the springs will reach like a well, that's their strength. You're like, okay, you know, you think of springs as like strong, you know what I mean, kind of only that max strength. Well, cool, yeah, when we take this spring and we really push on it, you know what I mean, then that's going to be its max. So we have a force max, but just never forget that the force min is 0 and it's linear. So those are the two things to think about, and then always be thinking, well, what's the average force? Well, it's just this force max divided by 2. This is force average. Okay, heck yeah. So so now how does this? Yeah. So the thing is right at the beginning, there's no force on the spring. You know what I mean? So let's say you move it a little bit. Think that there's no force. You know what I mean? You can move this. So M2 is going to drop for sure. It's going to drag M1. And if those two are the only two things, like we said, they're both going to fall and move. They're just going to move at half of free fall. I think we can imagine that. But now that we attach the spring, well, they're still going to move for half of free fall for a split second. You know what I mean? And let's say this is just a really long, loose spring. Maybe you could say that the spring has no force even after 1 second. You know, even after 1 second, you really didn't lengthen the spring compared to like a really, really long, loose spring. Okay, cool. And so, and always, for any physics problem, if you can make the system run for a second in your favor, where you're like, okay, I ran it for a second, and so we just did. We said this spring is just hella long, and then it's connected to mass 1. And then in 1 second, mass 1 is here, and we're just going to say, hey, this is just potatoes compared to like how long this spring is. And really, the spring hasn't changed length. There's still no force in the spring. Cool. So, so that's what we're getting at. We're getting at that we have, what I like to think of it is, well, I like to think of the difference in forces here as kind of like a driving force. So let's say, yeah, let's just say this is 10 kilograms. And what would mg be? Mg would be 1 times 10. So heck yeah, we have 10 newtons. So I'm going to say we have 10 newtons of force, but we have that on 2 kilograms. So we have 10 newtons on 2 kilograms. So what I do is like, we'll take 2 kilograms and drop it off a cliff. What would be the force on this? Well, it would be 20 newtons. So this is, hey, we only have 10 newtons on 2 kilograms. That's where we're going to have half of the acceleration. And you can imagine 10 newtons. Like 10 newtons, I think each newton is 1/4 of a pound. So this is like, well, oh, why isn't this? Yeah, this is tripping me out. Oh, I'm sorry. Yeah, 10. Yeah, because usually you have 1 kilogram and you'll have 10 newtons on 1 kilogram. Well, yeah, no duh, that's 2.2 pounds, you know what I mean? 10 newtons is 2.2 pounds, right? Because 1 kilogram is 2.2 pounds. And yeah, that's the force of gravity. The only reason that 1 kilogram even weighs 2.2 pounds is Kepler. That's why I get frustrated every time people bring up, well, no, I just think it's cool, you know what I mean? I'll take a win everywhere I can take a win, that I do something different that other people don't. It's just like, yeah, bring up Kepler's equation every time. Don't just say mg. You know what I mean? Every time you see an mg, just like friggin' write Kepler's equation. It'll do, because yeah, I mean, because you want to take your physics to Mars and other planets, and you don't want to be, it's claustrophobic, the fact that we live like just on like this tiny, or I mean just on the surface of the Earth, you know what I mean? It's such a narrow window of, you know what I mean, even for how big the Earth is. Anyway. Oh, hell. So, cool. So yeah, so just back to the problem, actually. Is that, yeah, we can run this for a second. Cool, they're in not free fall, kind of half of free fall. We envision that. And even after a second, there's no force on the spring. But after 2 seconds, hell yeah, there's going to be a little force on the spring. Now, do you think the little force on the spring is going to, if there was no force after 0 seconds, maybe there's only 1 Newton. How about, let's say, how about there's 5 newtons after a couple seconds? You know, I mean, we can kind of envision that. And after a couple more seconds, there's a total of 10 newtons. Cool. Okay, so even after we said like a couple seconds goes by, and then there's 5 newtons built up in this spring, well, cool. We had a total of 10 newtons driving 2 kilograms. Now we only have 5 newtons driving 2 kilograms. Let's break out our F equals ma just to see what that means. So we have a force of 5 newtons on 2 kilograms. Okay, we're going to actually rearrange. So if you're pro, you can just take F equals ma and just rearrange for acceleration, because that's usually what you want. So it's going to be force over mass. And hell yeah, we got 5 divided by 2. So now that's like 2.5. So now we have 2.5 meters per second. So now let's do a theoretical. So in 1 second, this system is moving 5 meters per second. You know, I mean, can't we do that? Because we said gravity is 10 if we had just one thing in free fall, but no, the free fall force of 1 is driving both masses. Cool, we had 5 when we didn't have the spring, and so that's what we have even after a second, because we're saying the spring ain't doing nothing after a second. Cool. So in 1 second, this stuff's up to 5 meters per second. After the second, oh, now we get to involve this. You know what I mean? Hey, yeah, we've identified a force, but hey, like okay, let's talk about this. So after the second, we're going to generate a 5 Newton force. You know, because let's say there was some slack in the spring for the first second, and then after this, during the second, we went from 0 to 5 newtons. Cool. So we have a total average force of 2.5 newtons over that second. You know what I mean? So that's what you can do, and so yeah, it's not going to be 5. So yeah, so we're just going to have a total. So it's So I think what you would do is 10 minus. Let's. Yeah, I want to make this. So after, how about this? After that second, we generate 10 newtons. What do we need? Oh, this is fascinating. Let's stick with that 5 newtons. Oh, now this is tripping me out. Alright, hell yeah. So what I'm going to go over is, like, you're not wrong to, you're not totally wrong to do this technique. Where you're just like, I don't want to do, like, the simple integration in my head. I just want to say, like, hey, there was no, like, yeah, there was no force on the spring for the first second. And then just magically the second, we just have a constant force of 5 newtons. Now, we know for a spring that's not true, like, because it's you have 0 and then you're building up to a max. You might have an average, but we're just gonna say after the second, you know what I mean, right after that, we're generating 5 newtons of force. So then we want to analyze just right then at that second. Well, we had that 10 newtons on 2 kilograms, but now we have a force this way pulling it back of 5. So we're going to have 10 minus 5. So now we still have a 5 newton force driving these two masses. So we still have 5 newtons driving these 2 kilograms, and so that's where we would have an acceleration of 2.5. So after that second, we still have an acceleration of 2.5. Now let's say at the third second, at 3 seconds, for whatever reason, the spring is now generating 10 newtons. Oh, this is cool. Like I don't really read the problems and ask what they want. I try to just like figure, I try to explain everything around it, and it usually gets me to the answer. It's just like, oh no, duh. They don't want to know. I was just thinking they want to know like when it moves constant velocity. Well, that's what we're getting to at second 3. At second 3, we have 10 newtons in the spring, and guess what? This has 10 newtons driving, so 10 minus 10. So now we have 0 newtons. And this means that our force is 0, our mass is still 2, but we have 0 meters per second squared. We have no acceleration. We've gotten up to speed, you know what I mean? And we could figure that out. And let's just kind of get, this is where I wanted to just guess. In the first second, we went 5 meters per second. Yeah, that was our acceleration. So cool, we're moving 5 meters per second. The second second, let's just say now we're changed our velocity by 2.5, but that's not true, so now we're going 7.5 meters per second, but that's not true because we'd be going, this is fascinating. So if you we could run a graph, but that's where I don't think you'd want to get hung up in the details like that. I think you can, because by not getting a precise answer, you're still kind of using a I think it's like a Newtonian method. Like if here's your graph, you're still just like, who cares? It's just stair steps. That's really all you're doing. So if you have an acceleration that changed from 5 to 2.5, your graph might look like this, but we're just doing stair steps and saying who cares. Alright, so hell yeah. So after the first second, we're up to 5 meters per second. After the second second, we're at 7.5. And the third second, well, hell yeah, magically we don't have any driving acceleration. So now our total velocity was just 7.5 seconds. But now let's keep running this. And after the fourth second, time is equal to 4. Let's say we're up to 20 newtons. And the force in this spring is linear. You know what I mean? If you stretch the spring or compress this, if you stretch this spring, you're going to generate, if you stretch this spring, you're going to generate that much force. And then you double that stretch, well, you're going to double the force. But with this time element, you know what I mean? This is, we can go from 0 to 5 to 10 to 20 to 40 newtons. Because why? Oh yeah, hell yeah. Because our velocity, if our velocity was constant, if you're just pulling a spring at a constant speed, well then you're going to have that change in length that's going to be like, okay, like it took this much force to get to here, it's going to take twice as much to get to there. So now your force is going to be linear. But with free-falling stuff, it's like, well, we said that our bummer. You know what I mean? I get mixed up on this, but because there's no force in the spring right off the bat, that first you're going to generate the most force in the shortest amount of time. Like that's what also from the the derivative perspective, like. Because you're going to have the most, like you're going to change your velocity the most, that means you're going to change this length the most right off the bat. And then once this force gets reduced, these Well, oh, no, 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 that's not true. Oh, this is fascinating. Like, sure, like you're going to get the most, the spring's going to lengthen the fastest right off the bat because you just have the, like what do we call that? But until this force equalizes, until you have 10 newtons in the spring, with that 10 newtons driving, until those equalize, you're still increasing your speed. And if you have acceleration, you know what I mean? Well, then you're still lengthening the spring, like constantly faster, and so you're going to be generating a force that's nonlinear. I think that's true. So that would be one of those statements where I'm just like, hey, I think what I just said was true, but who cares? Let's move on. All right, so hell yeah. So now let's talk about. So what did we do? So we got to second force. So let's just say we got to second force and we got 20 newtons in this spring. Well, guess what? The only driving force of 10. So now we have a net driving force this way of 10 newtons. And it's kind of like equal but opposite. So now our acceleration is going to be this way. And we have 10 newtons on 2 kilograms. And so, yeah, we have 5 meters per second this way. So what did we say after 3 seconds? We were up to 7.5. You know what I mean? Because we had the first second, cool. That second less. That third second, 0. You know what I mean? 0 change in speed, so it's still 7.5. The fourth second, now we're going the other direction, and we're going, changing our speed by 5. So then we're going to go back to 2.5. You know what I mean? Just for my little scenario. And let's say, yeah, then let's go up to 40. You know what I mean? Who cares? So we're going to go up to 40 newtons. We're going to have 30 newtons driving. And then our acceleration is going to be force divided by mass. And sorry for breaking on my calculator. 30 divided by 2. And so now we have 15. Yeah, people laugh at that. This is probably the second time I've divided 30 by 2. Anyway, hell yeah. So we have, now we have 15... No. 30 divided by 2. That's the acceleration. So now we're changing our velocity in that second by 15. So if we were still going 2.5 this way, we hella slowed down. You know what I mean? We're only going 2.5. But now in that second, we're actually going, so sorry to do this, 2.5 minus 15. Now we're going negative 12. Now we're going 12.5 meters per second the other way. You know what I mean? So in that, whatever that was, between the 4th and 5th second, if I got that right, that's when this thing's going to hit a dead stop. Cool. And that's why it's going to momentarily stop and then change directions. Okay, hell yeah. So, yep. And I don't know. We might as well, you know what I mean, this problem had 3 parts. And this is the, hey, derive an expression for the actual distance that it goes. And I have a cool way of doing that. And then the only other question, which we can probably just ponder, indicate whether the total mechanical energy of the spring block Earth. So sweet. I'm going to tackle this just briefly. And this is kind of where we can get esoteric. Indicate whether the total mechanical energy, and just know this is kinetic energy and potential energy. And yeah, I think, like, for all I know, that's it. Those are the mechanical energies. I think it's mechanical energy because it's not, I don't know what's non-mechanical. Electromagnetic, is that not mechanical? Anyway, but yeah. So the block spring Earth system, does it change as as this thing moves? And I don't think so. You know what I mean? And this is one where it's just like, cool, if you said changes, and I hope I'm just wrong, you know what I mean? Because that's where you're going to learn the most. Just instantly, like, figure out what your gut says, say whatever that is, you know what I mean? But for me, it does not change. And then explain why. And then it's just fascinating because a week later, you'll run across a video just being like, nah, I was totally wrong. But this is where I can definitely explain... we have F equals ma, that's cool. But then what I like is that you have the universe is made up of mass, and that mass has velocity. There's really nothing that's stationary. It's only stationary in reference to other things. So if we're on an Earth and we're kind of measuring something that's stationary, well, I mean, or like, hey, this table's stationary, but then there's something moving across it. Well, it's just like, you're just measuring a difference in velocity. You know what I mean? This definitely has a velocity of the table. That has a velocity, and they're probably going the other direction anyway. You know what I mean? Like, honestly, velocity of the table and the velocity of that mass, probably going the other direction, but you're just witnessing them going. They're probably going that way. You know what I mean? So that's the other thing. All right, so one aspect that I can, this is cool. I think this will be cool. Because this is where you can use physical fundamentals to someone's like, hey, can you do a thermodynamics? And I was just like, oh, that was probably the hardest class. I don't even know what thermodynamics is. But I've always pondered kind of what temperature is. And so here's an idea. Like temperature is a, this is cool. Because temperature is a something that we use to measure something that has mass. You know what I mean? You don't measure temperature on something that doesn't have mass. Like, you know what I mean? The temperature of I think the temperature of space would be nonsensical. Like if there's no mass to measure, I don't know. But anyway, for temperature though, so here's my model for temperature. Let's say we have one air molecule in a container. Well, guess what? Like that air molecule is moving. I think we can imagine that. And let's say there's only one of them, and let's say it's just moving in a circular path around this container. Well, from our you know what I mean? Hey, kind of like the F equals ma approach. If we have a mass and we have a constant velocity, well, cool. There probably is no forces. There could be no forces on it. You know what I mean? You could have a mass traveling at a constant speed across the universe, and it won't have a force on it. But the second you see that mass do like a roller coaster loop, hell yeah, it's got force on it. You know what I mean? The only way to get this mass to, you're basically like, and the quick answer is like, yeah, it has velocity that way, but it doesn't have velocity towards the center of the circle. You know what I mean? It has no velocity. At this point, it has velocity towards the center of the circle is 0. But because it's over here, it must have had some velocity towards the center. You know what I mean? So that's kind of the quick answer, and you must have a force. So the only way, so this is kind of cool, the only way to capture an air molecule that's moving, and let's say it due to, and it's moving around a circular container, the only way to hold it in there is to actually put a force like on it. So the container itself is applying that force. And if this container could not apply that force, like if the container just wasn't strong enough to hold one air molecule, well, that container would just get bigger and bigger and bigger. You wouldn't be able to contain it. Well, I mean, to a point, it would just be a straight line. You wouldn't have a container. But you could see where, you know what I mean, if this air molecule wins, maybe your container's getting larger because the air molecule is fast enough that the container can't, support itself. And so, yeah, that would be the idea of temperature. And, all right, hell yeah. And, you know what I mean? And this is cool because, like, I definitely want to get into more like, hey, what changes temperature? You know what I mean? Maybe photons. Photons hitting a chunk of mass and then vibrating it or exciting it. You know what I mean? Imparting its energy to that mass. I think that's what fascinates me. Can I take fundamental concepts of just like, hey, I have a mass that's moving across the universe, and if it's got a constant velocity, no forces. But if I kind of identify something about that mass, well, hell yeah, we got forces that did that. All right, hell yeah. And so we will end with kind of just my my brother actually took quantum physics. You'd think like I would know a damn thing, but no, not really. But that's what I want to study, the fundamentals of physics, and then move on to, you know, some of the basics of quantum physics, just to have an understanding. But so my take-home point on why the energy doesn't change is because as we know the universe to exist, is that we have, you know, whether you could look at the universe in a Newtonian perspective where, hey, let's just count up the mass and all that mass is moving. You know what I mean? That's a Newtonian. And my brother's like, hey, you can't neglect Newtonian physics. Like, if you want to learn quantum physics, definitely have a strong foundation of Newtonian physics and then move, you know what I mean, and then take a step into the quantum. You know, but never lose your touch of Newtonian physics. But yeah, that's a very sensical thing to do. Is just like, hey, we all know there's atoms, you know what I mean, after the Big Bang, you know what I mean, you have a lot of mass out there, and that mass is hella moving. So that's gonna be the energy biggie of the universe. All right, hell yeah! And now with the universe, you do whatever you want with it. You know what I mean? You can capture some of that mass, and and then you can use it for other things. You know what I mean? And move it around. All right, hell yeah. And so, okay, so that, I'm just going to leave it at that. So that could be a very Newtonian and classical way to think of things, is just like, hey, when I eat like food, you know what I mean, you got a little hot dog or something. Let's say all that food is moving around. Now, that's where it's not, and it is, and it isn't, you know what I mean? But just think about like, oh, all that food's moving around, and then when I eat it, now I can move around. And that seems basic, but it still is what's happening, even at the quantum level. We know that electrons aren't rotating orbitally around an atom, but we do know that electron has angular momentum. You know what I mean? And so we can see that's a physical property. And angular momentum is what the hell is angular momentum? It's a cross product between distance and linear velocity. So if an electron has angular momentum, then it has a cross product between distance. All right, hell yeah! I better leave it at that. Cool, electrons have angular momentum. But other than that, I don't know anything more about them. But I do know that an electron in itself isn't isn't energy. You know what I mean? So that's kind of fascinating to me. It does have angular momentum, but I'll have to explore more on that. But for this problem, I think total mechanical energy, let me see what they're thinking. We have no friction, so we don't have any heat loss due to heat or radiation. And so I think, but even if you did, you know what I mean? Like, isn't it just all... I mean, isn't that the second law of thermodynamics? Like, that in a closed system, and if the universe isn't in a closed system, like the total energy of the universe wouldn't change. So yeah, just the I guess I need to explore what mechanical energy is, and what they mean by mechanical energy. But hell yeah, this thing's going to oscillate back and forth. You know what I mean? If we do have a frictionless surface, there is no dampening to this. This thing is going to drop. It's going to stop and then go the other, stop and then go back the other direction. And it's going to go back to the starting position. So if it starts here, stretches, is just going to go back and forth, oscillating like that forever. So I don't know. Is that what they mean by total energy doesn't change? Because this thing isn't being dampened. But anyway, alright, I better get to bed, so thanks for joining me for this one, and guess what? That's a video.